Hello, welcome back to my tech farm. I'm Igor and I have another filament testing video which is actually created thanks to my viewers who give me a suggestion to try extruder filaments. So I contacted them and they decided to send me. These are the PETG, XPETG with carbon fibers and PCTG filaments. And these four are the flexible filaments. So we have here semi-soft, medium and two TPU filaments which are hard, but this one has carbon fibers in them. But these four will be tested in a separate video. In this video I am testing these three and I will do all those mechanical testing which I usually do in this video. The results you can download from my website, but for Patreon supporters, as always, I am adding these three lines to that summary table and they can compare very easily these results to those which I did in earlier videos. Let's take a closer look. This is PETG in gray color and the printing temperature between 210 and 230 degrees Celsius. XPETG, which includes the carbon fibers in them, and the printing temperature is between 220 and 240 degrees Celsius. And this is PCTG in navy blue color, and the required printing temperature is between 250 and 270 degrees Celsius. And for carbon version we have to use a hardened nozzle, and according to the website at least 0.5 mm in diameter, but I think I will try to do some test prints with 0.4, so the results are comparable with each other. The temperature tower will be from 230 to 210 degrees Celsius, and here you can see the packaging. There is some silica gel inside. I'm missing here some information about the temperature. As I can see, this is 1.1 kilograms spool. So I will write the temperature on the spool with the marker. And I will print everything on my Prusa MK3S where I have installed hardened nozzle. I will use hardened nozzle for all three filaments in this video. And I'm using Extrudr PETG sheet, which I really like for printing with PETG. And I'm starting on 230 degrees Celsius for this PETG printing. And at 210 degrees Celsius I noticed a problem, and I believe because of the weaker layer adhesion, because I'm using maybe a hardened nozzle, on lowest temperature the part of it didn't stick too good. Material sticks good, but when the bed cools down it is very easy to remove it. So as you can see, this temperature tower looks okay except of this part, which I believe that weaker layer adhesion is the problem, but we will see that in the layer adhesion test. All test objects I will print on 230 degrees Celsius. And as you can see, I'm printing all test objects at once. And these are last two elements for the layer adhesion test. And I'm storing PETG in the resealable bag with some silica gel inside. Next one is PCTG, and the temperature tower in this case will be from 270 to 250 degrees Celsius. And this is 0.8 kilograms spool. And it sticks good to the bed using a little bit higher temperature on the bed, and here I can see the bridging moment. And this temperature tower looks great on all three elements. And same thing here, sticks very good to the bed, and when it cools down, just flexing a little bit and it is removed. Perfect overhang, bridging, but here I will print everything on 270 degrees Celsius. And again, all test objects will be printed at once, and this printing was also without any problems. Last two elements for the layer adhesion test. And all test objects are ready, and same thing, storing in the resealable vacuum bag. Next is the carbon version of the PETG. Pay attention, here we have only 800 grams of the material. And the temperature tower will be from 240 to 220 degrees Celsius. I already mentioned that with carbon filaments we need a hardened nozzle, but also according to the website we need 0.5 mm diameter nozzle or bigger, and I directly asked the extruder if I can try to print it with 0.4. Well, they told me with the shorter printing maybe yes, but they definitely recommend 0.5 mm nozzle or bigger. Well, anyway, I will try with 0.4, but I will be continuously here to follow the printing, because if I hear that the extruder is skipping, maybe I have a clog and I have to stop the printing. I want to use 0.4 mm nozzle because I want these test objects to be more comparable with each other. This is the start of the temperature tower without any problems, sticks good. And look at this perfect printing, absolutely no problems on any elements. Real beauty. I really like this. Any carbon filaments will give a really nice looking. Look at this perfect overhang, bridging. And I will print everything on 240 degrees Celsius. So I started the printing all test objects at once. And here actually the problem started. I didn't notice immediately, because after approximately 10 millimeters, when all test objects are printed except these two, I had a clog in the nozzle. I tried to clean it using the needle, try even some cleaning filament, cold pull, but I ended by replacing the steel nozzle with the brass one. I'm adding this info to spool to remind me that I need 0.6 mm nozzle. So this is ND3V2, where I have already installed 0.6 mm hardened nozzle. And I will here print those two vertical test objects for the layer adhesion test. But basically with new adaptive layer width with the Prusa slicer or Cura, I will have very similar final solid objects. And this time the printing was without any problems, and really nice test objects I got with this printing. I know I should listen to the manufacturer's advice, especially after they give me this warning in the email too, that I should use a 0.5 or bigger hardened nozzle. But I was hoping, because recently I tested some carbon fiber ASA, and there I asked also the company, and they told me that the warning on the website is just for their safety, because they have the similar specifications for the recommended nozzle. But they regularly print on 0.4 mm nozzle without any problems. And yes, with that material I printed maybe 20 or even more hours without any problems. Well, here, lesson learned. I ordered a new hardened nozzle because I don't want to clean this, and I will pay attention next time. But I also want to do a little bit more printing with this, so I'm printing some brackets for the shaft, and I need 8 pieces of these, and the total printing time will be almost 20 hours. So I hope that will be without any problems. And I'm starting with the mechanical test. This test object is printed horizontally for the tensile or pulling test, and I'm starting with PETG. These values are average for the PETG. Don't forget, it is not so strong like PLA, but it has some other advantages. This one is PCTG, and this is the carbon version of the PETG. I will show you our results later in a summary table. But basically they broke very similarly. Next one is the layer adhesion test with the vertically printed objects. Smallest cross-section area is 4 by 4 mm, and I'm starting with PETG. Little bit low values, but I will talk about this later. The next one is PCTG. Still below 20 kilograms, which I consider as a low value. This is the carbon version of the PETG. And a little bit above 20 kilograms. This is the final result. They didn't even broke equally, but the cross-section area looks very solid in all 3 cases. I think I need a little bit more testing with this. I need one more testing for my curiosity, because all test objects are printed using hardened steel nozzle, and I have that feeling that here the layer adhesion is much weaker. You saw on that PETG temperature tower on 210 degrees Celsius even part of the object broke down because of the weaker layer adhesion. And I'm curious now, since I removed to the brass nozzle anyway here because of that clog with carbon filament. I'm reprinting these test objects for layer adhesion. This is from the PETG, and from PCTG is in progress now. And I'm curious if I will have better layer adhesion if I use completely same settings for the printing. Usually the PETG I'm printing on higher temperatures. 245 is in Prusa slicer by default. I use 240 because officially this is the upper limit on the recommended temperature range. And now let's repeat that layer adhesion test. This is PETG. And this time about 20 kilograms. And this is PCTG. And this time this was also about 20 kilograms. And this is how they look like, and even for the feeling, I would say that the layer adhesion is still quite weak. Well, after this I needed one more experiment. So during this testing of the Sobol SV06 Plus, which is able to print up to 300 degrees Celsius, I printed these new test objects for the layer adhesion test, which doesn't have a hole. But only when I tried to remove them, one of them broke down because the layer adhesion was too weak. But I printed them on 250, 270 and 290 degrees Celsius for the comparison. And of course, as I expected, on 290 degrees Celsius I had a lot of stringing, which I expected actually, because this is 20 degrees Celsius above recommended printing temperature. But let's do the testing. I'm starting with parts printed on 250 degrees Celsius. These are my new holders. They are CNC machined by PCBWay. I use their services this time, and here you can see how they work. And these on 250 degrees Celsius, I think they are quite weak. Even these printed on 270 degrees Celsius are not so strong like those on Prusa. I'm not sure why, maybe because I printed them faster, or maybe I printed 4 at once. Even these on 290 are stronger, but I think they are not strong enough. And I have to test my new equipment, so this is just a regular PLA for reference. And as you can see, it broke almost at 60 kilograms approximately, so everything is okay with this equipment. Two-sided shear stress. The diameter of this test object is 5 mm, and I'm starting with PETG. And this is quite good value, basically average for the PETG. Next one is PCTG. Very similar values I've got here. This is the carbon version of PETG. And this one was the strongest in this test. All three test objects shared correctly, only darker the color it is harder to find all three elements. And now torque or twist test. The diameter of this test object is 6 mm, and I want to measure the load at 90-degree angular rotation and the maximal load, and I will do it with this torque meter. 0.8. 0.8. 1.1. And now I think broke. And 1.1 was the peak. 1. 1.3 was the peak. Interesting, 3 different breaks. Surprisingly, the PETG was very brittle, but probably because of the weaker layer adhesion. For the deformation, the PCTG and carbon were similar, but they break on different load. And now my 3-point bending test, where I'm measuring not only the load, but also the deformation after 1, 30 and 60 seconds. And here you can see the loads. In a video I will show you only the deformation after 30 seconds, but in a summary table you will see all those deformations. And here they are side by side on 1.25 kilogram load. This is on 2.5 kilograms, 5 kilograms and 10 kilograms, everything after 30 seconds. And no visual deformation after this testing. Now let's see how brittle are these materials with this ISO impact tester and the half kilogram hammer. And the tougher the material, it needs more energy for the break, and the hammer will swing to the lower position from the 0, but I think I should explain this in a separate video. Now let's do the measuring. PETG, 0 position, PCTG, carbon. The scale, and this is the 0 position of the hammer, and this is after breaking the PETG test object, and this is after PCTG, and between them is the carbon. So basically very similar materials, but from these three the PETG is the most brittle, and if I measure everything from the 0 position I will get these values. This is the age in this calculation, but I have to insert it in the meter, and I will get the breaking energy in kilojoules per square meters. And this is my regular creep test, where I have these C test objects, and I will place a 1.25 kilogram load on them. The first one is from PETG, this is the PCTG, and this one is from carbon. I'm locking the position for more accurate measuring. I'm measuring the distance between reference surfaces, which is without load 12 millimeters. But even without measuring, we can see that the biggest deformation is on the PCTG and the smallest is on carbon filament. And after this, I will measure them every day, but off camera. And here you can see picture recorded once a day. So this is day 3, day 4, 5, 6, and the last one, the 7th day. And now recording the removing of the load. And this time I didn't place them in the oven for the additional deformation. And here you can see their deformation. So the smallest on carbon and the biggest on PCTG. And now the temperature test. And I have here this M10 nut as a small load. And I want to record the temperature on the first deformation. And here you can see my cooking thermometer. This is speed up video, but now let's see it a little bit slower. So the first deformation I noticed on PETG. And then the PCTG and carbon deformation was very similar. And for the filling, basically after, let's say, half minutes, they are very similar, but the biggest deformation I can see on PETG. On the website, they claim that PCTG is a scratch-resistant material. Well, let's try to test this with these sharp tweezers. Under the microscope, this is the PETG, and this is the PCTG, and this is the carbon PETG. And actually I cannot see any difference between them under the microscope. Not a scientific approach, but let's try to measure something. So this is a short D durometer. It has this sharp needle which will penetrate into material, and it measures how deep it goes into it. And this is my test equipment. I'm starting with PETG. The average is 68.2. This is PCTG, and yes, it is harder, so theoretically maybe it is more scratch resistant, but the carbon version, probably thanks to those carbon fibers, is even more harder material. And now let's analyze the data in this Excel table, which is downloadable from mytechfun.com website. And for Patreon supporters, as always, I'm adding these 3 lines to that summary table. Okay, let's start with the creep test. So this is the raw data, measured the difference between these 2 reference surfaces. But what we need is the difference between 2 days, and that's why I prepared this table. 0 means no creeping, no deformation. And if you analyze this on this graph, we can see that PCTG had the biggest creeping on first maybe 2-3 days, and only after 4 days it stopped with the deformation. The best in this test was the carbon version of the PETG. Basically, almost after first day it stopped with the deformation. There are small negative values here, but that may be inaccuracy in measuring. The tensile test, everything is okay here. Average values for the PETG version of the filaments. And now that layer adhesion test. So here you can see these 3 numbers are printed with hardened nozzle, and then I reprinted them with the brass nozzle using the same G-code basically. And here you can see that interesting, the layer adhesion is better, but quite low values. So 20 kilograms, that's quite low. And for curiosity, I printed these test objects in vertical position, 4 at a time on that Soval SV06 Plus. And here I got even weaker layer adhesion. I'm not sure, maybe because it was printed faster or 4 at once or something like that. But this is first time I'm using this kind of test objects. The cross-section area is the same, 4 by 4 millimeters. So for testing, I printed this reference PLA, and as you can see, it broke very similar to that break which I already tested this earlier. Shear stress, average values, so no surprises here. It doesn't depend from the layer adhesion. And now the bending test. So in this table we can see the deformation on these loads after 30 seconds. And here we can see that smaller values are better, so less deformation. The carbon version was the best in this test. And if we analyze this table, where we have the deformation after 1, 30 and 60 seconds on this given load. Good values are when we see horizontal values. We can see on this graph that it is a little bit under the angle. This means we have this creeping during this 1 minute of the testing. So in this test, again, the carbon filament was the best. On the torque test, you saw the PETG broke too early after maybe 40-45 degree angle, so it couldn't do 90 degree rotation to see that load. So in this test, the carbon was the best. And then the impact test, and what I predicted, so the PCTG is the best in this test and PETG is the most brittle, but I thought the difference will be much bigger here. The temperature test, almost what I expected, but I was hoping that we will have a little bit bigger temperatures here. So on the lowest temperature was the PETG, which started to deform on 61 degrees Celsius approximately, and PETG and carbon were very similar, approximately 75 degrees Celsius. And well, you saw the hardness test. Actually, yes, the PCTG is harder than PETG, but the carbon, properly thanks to those carbon fibers, even better resists to the penetration. So in this test, it was the hardest. Don't forget, this is not completely linear scale, so the difference is a little bit bigger than we can see it here. And then last is the price, which depends, may differ, depend of the country. But what I saw for me, for example, if I would buy it, these are the prices in euros. But don't forget, from PETG we have 1.1 kilogram on the spool, from these two 0.8. So if I calculate euros per kilogram, then basically the carbon is far expensive and the PETG is a little bit cheaper compared to the PCTG. Just some additional information I recorded later. I noticed on the website we can buy bigger spools. In that case, price per kilogram is a little bit cheaper. And also I find that the weight of their spools is a little bit hidden on the website. It's inside the PDF which we have to download. So this picture is from that PDF, and in this row we can find the weight of the spools. And other conclusions. Well, based only on my experiments, the biggest advantage of the PCTG over the regular PETG is the temperature resistance. So you saw 15 degrees Celsius almost, that's quite important. But watching other mechanical properties, they are quite equal, or sometimes the PCTG is even weaker. But in all three cases, I noticed a little bit weaker layer adhesion. So you have to keep in mind this when you are creating designs and the orientation of the printing. For example, this kind of shelf holders should be printed in this position and never in this position. But definitely from these three, my favorite is the carbon version. It has even the biggest layer adhesion using the same nozzle. And don't forget, you have to use 0.6 mm nozzle to avoid clogs during the printing. Perfect looks of the printing. Let me show you again that temperature tower. And I already mentioned that I want to do more printings because I want to see if everything is okay with 0.6 mm nozzle and this carbon filament. And I use almost the whole spool. That's why I was searching for the weight of the spool to see how much filament I have on it. And I printed these shelf holders. This is a second set because originally first I wanted to print it from ASA, and since I'm using 0.3 mm layer height, I couldn't have nice printings with ASA. I always had this warping, you know, if you're not familiar, bigger layer height, more tendency to warping. And these are perfectly straight, great printings, but again, don't forget, use a bigger nozzle, not 0.4 mm. And as always, the results are downloadable from my website. For my Patreon supporters, I'm adding these three lines to that summary table so they can easily compare these materials to those which I did in earlier videos. This is my only gift to my Patreon supporters, so thank you all for the supporting. And if you have some additional experience with these materials, you know, a few lines in the comment section. And in a few weeks, I will publish the video about the Extrudr TPU filaments I mentioned at the beginning. Thank you for watching and happy printing!